The biggest galaxy in the universe is bigger than your imagination. There is a galaxy out in the deep cosmos so staggeringly enormous that the human brain genuinely cannot hold its true scale all at once. That is not a figure of speech or a dramatic opener designed to pull you in. It is a straightforward description of what happens when you try to place genuine cosmic measurements next to the kind of spatial understanding our minds were built to handle. The object in question sits more than 1 billion light-years from where you are right now, suspended in the dark between other galaxies, glowing faintly with the ancient light of more stars than any civilization could ever count. And yet, here we are, a species on a small world orbiting an ordinary star, trying to make sense of it. You might already feel like you have some grasp of cosmic scale. You have probably seen comparisons showing how tiny Earth looks parked next to Jupiter, or heard that 1 million Earths could fit inside the Sun. Maybe you know that our own Milky Way galaxy spans roughly 100,000 light-years, from one edge to the other. Those are remarkable numbers, but the moment you look deeper into the universe, beyond our own galactic neighborhood, the comparisons you relied on start to feel dangerously small. The scale keeps extending, rung by rung, into territory that no human experience can truly prepare you for. So before we arrive at the giant waiting for us in the deep dark, we have to build our way there carefully. We need to take each step of the scale ladder seriously, because the only way to appreciate something genuinely incomprehensible is to understand exactly why it exceeds everything that came before it. If you enjoy exploring the strangest and most breathtaking corners of the cosmos, subscribe and hit the like button before we dive in. Let us begin where all human experience begins. On the surface of Earth. Earth feels enormous. The entire history of our species has unfolded on this one world. Every civilization, every war, every discovery, every artwork ever created happened on this single rocky surface wrapped in a thin skin of atmosphere. It feels like a substantial place. By the measures of human experience, it genuinely is. But cosmic scale does not care about human experience. Place Earth beside a Jupiter, and our home planet immediately transforms from a world into a pebble. Jupiter is so large that roughly 1,300 Earths could fit inside it by volume. Its most famous storm, the Great Red Spot, is a swirling system larger than Earth itself. It is a planet of extraordinary dimensions, and yet it is just a planet circling one ordinary star. The moment you shift your attention from planets to stars, even Jupiter begins to look small. Our sun dominates everything we know. It lights our sky, drives our weather, and powers every photosynthesizing organism that has ever lived on this planet. It contains approximately 99.8% of all the mass in our entire solar system. More than 1 million Earths could be packed inside it. For most of human history, it was worshipped as a god. And in purely instinctive terms, that reaction was completely understandable. Except that the sun is not special. Not cosmically. It is a fairly average star, one of hundreds of billions packed into the Milky Way galaxy alone. The burning lamp that makes all life on Earth possible is, from the universe's point of view, completely ordinary. One grain of light among an enormous field of similar grains. The distances between those grains are where space first starts to feel genuinely strange. The closest star to our Sun, Proxima Centauri, is more than 4 light-years away. Light itself travels at nearly 300,000 kilometers per second, fast enough to circle the entire Earth more than 7 times in a single second. And even at that absurd speed, it still takes over 4 years to reach our nearest stellar neighbor. If you shrank the sun down to the size of a grain of sand, the nearest equivalent grain would not be inches away or even feet away. It would be miles distant. That is the actual architecture of the cosmos. Not crowded, not packed. Astonishingly, almost incomprehensibly empty, with brilliant points of light separated by gulfs of black space that stretch far beyond ordinary intuition. And yet all those scattered stars, all those solitary lights drifting through enormous distances, belong to something even larger. They belong to a galaxy. Our Milky Way is not simply a large collection of stars loosely grouped together. It is a vast rotating structure of stars, gas, dust, and dark matter, organized into a central bulge and sweeping spiral arms that curve outward across space like luminous rivers. Somewhere in one of those quieter outer arms sits our Sun, roughly 26,000 light-years from the galactic center, traveling at tremendous speed and still requiring approximately 230 million years to complete a single full orbit. To put that in biological terms, the last time our solar system occupied this same position in the galaxy, dinosaurs had not yet appeared on Earth. The Milky Way contains hundreds of billions of stars. Each of those stars might have planets circling it. When you look up at the hazy band of the Milky Way on a truly dark night, you are not seeing mist or atmospheric haze. You are seeing the combined light of a structure so immense that it takes light 100,000 years to cross it from edge to edge, and yet the Milky Way is not the universe. It is not even close. That realization was one of the great turning points in the history of human thought. For a long time, the Milky Way was assumed to be everything, the whole of the heavens. Then telescopes improved, and the faint blurry smudges that careful observers had noticed scattered across the night sky slowly began to reveal their true nature. Those fuzzy patches were not clouds floating inside our galaxy. They were galaxies themselves, entire systems of stars, gas, and dark matter lying far beyond the Milky Way, each one an island universe carrying billions of stars of its own. The universe did not end with the Milky Way. The Milky Way was only where we started looking. Beyond our galaxy lie neighboring galaxies, then groups, then vast clusters containing hundreds or thousands of galaxies, then superclusters, then the cosmic web itself, a grand filamentary structure stretching across the entire observable universe. At that scale, the Milky Way is one neighborhood among an almost unimaginably large number of others. And here is where things become truly interesting for our story, because galaxies do not all come in the same size. Some are dwarf systems with only a few million stars, fragile and loosely organized. Some are spirals like our own, structured and luminous. And then, at the centers of the largest and richest galaxy clusters, there are the giants, galaxies that have spent billions of years growing by pulling in smaller neighbors, consuming them, and adding their stars to swelling halos of diffuse light. These are not simply bigger versions of the Milky Way. They are fundamentally different objects, shaped by a history of repeated mergers and long cosmic accumulation, smooth and swollen where spirals are structured and elegant. Among those giants, a few stand so far above the rest that even astronomers have to be careful about the language they use to describe them. One of those objects is IC 1101. IC 1101 sits at the heart of a galaxy cluster called Abell 2029, more than 1 billion light-years from Earth. For many years, it has been one of the most frequently cited candidates for the title of the largest visible galaxy. Known for its immense stellar envelope, its extraordinary depleted core, and its position as the dominant central member of one of the most massive galaxy clusters in the nearby universe. Modern measurements have refined the picture somewhat. The older, more sensational numbers that circulated in popular descriptions, figures claiming IC 1101 stretched 4, 5, or even 6 million light-years across and contained around 100 trillion stars, were larger than careful current analysis supports for its bright central regions. But surrounding that denser core is a diffuse outer halo that extends so far into the surrounding cluster environment that the boundary between the galaxy and intergalactic space becomes genuinely difficult to define. IC 1101 is less a sharply bounded object and more like a continent of light that gradually dissolves into the surrounding darkness. That quality, the absence of a clean edge, makes it even stranger to contemplate. A galaxy with a clear boundary can at least be mentally contained. IC 1101 resists that containment. Its outer regions blend into what astronomers call intracluster light, a faint, diffuse glow produced by stars that were stripped from other galaxies during ancient gravitational encounters and now drift freely through intergalactic space. The central giant sits inside this enormous stellar fog, making the whole structure feel less like a single isolated object and more like the luminous core of something far larger. But how did it become this way? The answer is a story about gravity, time, and the relentless logic of cosmic accumulation. The story of IC 1101 does not begin with a dramatic revelation. It begins with a faint smear of light. On June 19, 1790, the astronomer William Herschel recorded a dim object in the constellation Virgo while scanning the sky with one of the finest telescopes of his era. To him, it was one more mysterious patch among countless others, a fuzzy spot that could have been almost anything. He could not have known that the light entering his instrument had been traveling through space for roughly 1 billion years before reaching his eye. He could not have guessed that the smudge he noted in his catalog was one of the most colossal stellar systems in the observable universe. Discovery in astronomy almost always begins exactly that way. Not with certainty, but with a shape barely glimpsed through the dark. For most of human history, the night sky was more myth than map. The faint cloudy shapes scattered among the stars were called nebulae, a word meaning simply clouds. No one knew whether they were near or distant, small or enormous. They were just there, soft marks on the darkness, noted and catalogued and largely unexplained. IC 1101 lived in that category for many generations. It was observed before it was understood. That is one of the most compelling things about the history of astronomy. The sky reveals itself in layers. Humanity first learned that the planets were worlds, then that stars were suns, then that the Milky Way was a galaxy, and only then came the deeper shock that those faint nebulae were galaxies of their own, entire island universes lying far beyond anything anyone had previously imagined. When that understanding arrived in the early 20th century, it transformed the scale of perceived reality almost overnight. The Milky Way was no longer everything. It was one galaxy among many, one city of stars among uncounted others. Once that door opened, objects like IC 1101 became something entirely new in the human imagination. They were no longer unidentified smudges. They were systems with structures, histories, and masses that could be studied and organized into a hierarchy of cosmic forms. And that hierarchy revealed something unexpected. Not all large galaxies are graceful spirals. Some are smooth and rounded ellipticals filled with old stars. And at the centers of the richest galaxy clusters, astronomers kept finding the same thing: enormous central galaxies so dominant that they seemed to rule entire galactic kingdoms from the deepest point of their cluster's gravitational heart. IC 1101 was one of those rulers. To understand how IC 1101 grew to its present scale, you have to abandon the idea of galaxies as fixed and permanent objects. They are not statues placed in space and left unchanged across cosmic time. They are dynamic systems, always moving, always responding to the gravitational pull of neighboring matter, always capable of being reshaped by encounters with other galaxies. When two galaxies meet, they do not collide the way cars do on a highway. The stars inside galaxies are separated by such extraordinary distances that direct stellar collisions are vanishingly rare. What drives the encounter is gravity. Gravity reaches across space like an invisible hand, tugging simultaneously on billions of stars, bending their paths, drawing long streams of light out into the surrounding dark, and gradually dismantling the distinct identity of each galaxy until two separate systems become one. If you could watch a galactic merger on fast forward, it would look less like an explosion and more like a slow dance, gradually collapsing into turbulence. Two galaxies approach from far apart, each carrying its own shape and internal rotation. Gravity begins to distort them. Stars are pulled into long curving arcs, gas clouds are compressed and twisted. The orderly structure of each galaxy stretches like soft material under persistent pressure. A single close pass is often not enough to complete the merger. The galaxies may swing past each other and then return, bound together by gravity that refuses to let either escape. Each subsequent pass steals more of their original structure. Over hundreds of millions of years, the encounter deepens, spiral arms unravel, gas rushes inward and ignites bursts of new star formation. Long ribbons of stars called tidal tails are flung far into intergalactic space. Then finally, gradually, the two systems merge completely. Their original forms vanish. What remains is a single larger system, rounder and smoother than either of its parents, an elliptical galaxy born from the death of two spirals. Now imagine that process not happening once, but again and again over billions of years, to a galaxy sitting at the center of one of the richest gravitational environments in the known universe. That is the situation of IC 1101. The galaxy at the heart of Abell 2029 occupied the perfect position for sustained, relentless growth. It sat at the bottom of a deep gravitational well, the point toward which the motion of nearby galaxies naturally tended over long timescales. Galaxies moving through the cluster gradually lost energy through interactions with the surrounding gas and dark matter, causing them to slowly drift inward. The central giant was there waiting when they arrived. Some of those incoming galaxies were stripped apart before completing a full merger, their stars scattered into IC 1101's growing outer halo. Others merged more completely, pouring stars, gas, and dark matter into the central system. Every encounter left a mark. Every mark made the galaxy a little more extended, a little more dominant. This is what IC 1101's enormous diffuse outer halo records, that faint envelope of light extending so far that it blends into the surrounding cluster environment, is not a mystery. It is the accumulated residue of countless smaller galaxies consumed across billions of years. It is the galaxy's entire violent history made visible, spread across millions of light years of space. If the outer halo tells the story of what the galaxy collected, the center tells the story of what it destroyed. Astronomers examining the core of IC 1101 have found something unexpected. The central region is unusually depleted, meaning there are significantly fewer stars there than standard models predict for a galaxy of this mass. The center should be densely packed with stellar light. Instead, it is strangely empty, carved out into a vast low-density cavity unlike anything seen in smaller or simpler systems. The most compelling explanation involves black holes. Every large galaxy harbors a supermassive black hole at its center. When two galaxies merge, those central black holes both sink toward the middle of the newly combined system. At first, they orbit separately through a dense surrounding population of stars. Gradually, they draw closer and form a gravitationally bound pair, circling one another in progressively tightening loops. As that orbit shrinks, they begin ejecting nearby stars outward through gravitational slingshot dynamics. Stars that passed too close to the spiraling black hole pair can be hurled outward at enormous speeds, thrown entirely out of the core region. This process repeats with every major merger. Stars are steadily cleared from the center. The core becomes progressively more depleted. After billions of years of accumulated mergers, what remains is a region so large and so empty of stars that it rivals the scale of entire small galaxies. In IC 1101, the depleted core is thought to be among the largest ever measured anywhere in the universe, a scar left by not one but many successive black hole encounters across the full depth of cosmic history. The galaxy, therefore, carries a paradox at its heart. It is one of the most massive stellar systems ever studied. Yet its very center has been cleared out by the same violent process of repeated mergers that built the rest of it. Growth and removal happen simultaneously, driven by the same engine, Addition and subtraction operated together as part of the same long cosmic machine. Hidden inside that depleted core is a black hole of extraordinary scale. The Milky Way's central black hole contains roughly 4 million times the mass of the Sun. That is already a number that resists intuition. 4 million solar masses compressed into a region comparable in size to our solar system, with gravity so extreme that beyond a certain boundary nothing can escape. Not matter, not radiation, not light. And yet 4 million solar masses is modest by the standards of the largest galaxies. The black hole believed to reside at the center of IC 1101 belongs to a category astronomers refer to as ultramassive, a term that exists specifically because supermassive no longer sounds extreme enough. The estimated mass may reach tens of billions of solar masses. The difference between 4 million and tens of billions is not simply arithmetic, it is a categorical leap, like comparing a hill to an entire mountain range. For an object this massive, the event horizon would extend across a physical region comparable to our entire solar system or larger. The dark center of this galaxy is not merely powerful in some abstract gravitational sense. It is spatially vast in a way the spatial imagination has almost no framework for handling. But a black hole does not sit passively doing nothing. When matter falls inward toward a black hole, the region just outside the event horizon becomes extraordinarily energetic. Powerful jets of particles can be launched outward at speeds approaching that of light, punching through the surrounding gas of the galaxy and the cluster beyond. When those jets push into the hot gas filling Abell 2029, they can inflate enormous cavities, bubbles of hot plasma blown into the cluster's gaseous atmosphere by the energy released near the black hole. Those bubbles rise, expand, and heat the surrounding gas as they go. This has significant consequences for the entire system. The hot gas filling the cluster could in principle cool down over time and fall inward, potentially forming new generations of stars. But if the black hole keeps injecting energy into that gas and reheating it before it can cool, that process is continuously disrupted. The black hole acts like a thermostat for the entire cluster. Too much cooling and star formation would accelerate dramatically. Too much heating and the gas remains permanently too warm to collapse into stars. In IC 1101, the balance has tipped firmly toward heating. The galaxy is surrounded by an enormous reservoir of material, but that material cannot easily settle into new stars. It is in some ways a great empire surrounded by resources it can no longer efficiently harvest. This deep relationship between a galaxy's mass and its central black hole is one of the most important discoveries in modern astronomy. Larger galaxies consistently host more massive central black holes. The connection is too strong to be coincidental. It suggests that the growth of the galaxy and the growth of the black hole are fundamentally linked. As mergers added stars and matter to IC 1101, they simultaneously fed the dark engine at its core. And as that engine grew more powerful, its energy output increasingly shaped how the rest of the galaxy evolved. One built the other. One restrained the other. Two partners locked in a billions-year negotiation, each continuously reshaping the other's fate. No galaxy as large as IC 1101 grew to its current dimensions by accident. Its location within the universe was as important to its development as the time it had available to grow. On the largest observable scales, the universe has structure. Galaxies gather into groups. Groups gather into clusters. Clusters connect along enormous filaments of dark matter and hot gas. Between those filaments lie vast voids, regions of space so nearly empty, they make the distances between individual stars seem comparatively crowded. Astronomers call this arrangement the cosmic web, one of the most remarkable things that observation of the deep universe has ever brought into view. A galaxy cluster like Abell 2029 is one of the main gravitational nodes of that web. It is not simply a crowd of galaxies seen in the same direction by coincidence. It is a real gravitationally bound system containing hundreds of galaxies, all immersed in a vast reservoir of superheated gas glowing at X-ray wavelengths, and all embedded within an even larger halo of dark matter. Most of the cluster's actual mass is either in that hot X-ray gas or in dark matter that reveals its presence only through its gravitational effects. Abell 2029 is one of the most massive known clusters in the nearby universe. Its total mass has been estimated at more than 100 trillion times the mass of our Sun. Its reservoir of hot gas is so extensive that it effectively surrounds IC 1101 like an invisible atmosphere stretched across millions of light years in every direction. The galaxy sitting at the center of such a system has a profound long-term advantage that no galaxy in a quieter environment can match. It occupies the bottom of a gravitational basin. Over billions of years, everything that moves through the cluster and loses energy tends to drift inward toward that lowest point. Stripped stars, disrupted smaller galaxies, diffuse streams of gas, all of it gradually settles toward the center. IC 1101 has spent billions of years at that collection point, accumulating patiently what the cluster continuously delivers. This is why the Milky Way, for all its hundreds of billions of stars, cannot grow into something resembling IC 1101. Our galaxy lives in a small and relatively quiet group. It does not sit inside a massive, rich cluster. The deep gravitational environment that turns an already large galaxy into a true titan simply does not exist in our corner of the cosmos. To build a galaxy like IC 1101, the universe needs not only time but the right address. A location deep within a rich cluster, at the gravitational collection point of an environment that keeps delivering material across cosmic ages. A quiet neighborhood produces a different kind of galaxy. A crowded and deep cluster center produces something else entirely. In the universe, where you live determines what you are capable of becoming. Even something as immense as IC 1101's is not permanent. That may be the most difficult thought in this entire story to absorb. We tend to associate extreme size with extreme durability. Something as colossal as a stellar system, more than 1 billion light-years distant, seems like it ought to endure essentially forever. But the universe does not protect its largest structures from change. It simply takes longer to change them. The universe's expansion is ongoing, and it is accelerating. Something astronomers call dark energy is driving space itself to expand at an increasing rate. The effect on the largest scales is that galaxy clusters, which gravity holds together locally, are becoming progressively more isolated from one another. More of the broader universe is being carried beyond the observable horizon. The cosmic web will remain intact within its local gravitationally bound pockets, but those pockets will become islands in an ever-widening sea of unreachable space. Within the galaxy itself, the future unfolds more slowly but just as surely. The bright blue stars, the short-lived massive ones that burn hot and die young, are already long gone in a galaxy as old and evolved as this one. What remain are the more patient stars, smaller and cooler, burning steadily across enormous timescales. The smallest red dwarf stars can shine for trillions of years, far longer than the current age of the universe. The galaxy's light will not go out all at once. It will fade gradually, dimming as each generation of stars exhausts its fuel, cools into white dwarfs, and drifts quietly through the aging halo. The supermassive black hole at the center will be among the most persistent objects in the system. Long after the last ordinary star has exhausted its nuclear fuel, the black hole will remain. But even then, according to theoretical physics, black holes are not perfectly eternal. Through a slow quantum process known as Hawking radiation, black holes can gradually lose mass over timescales so immense that writing them numerically strains the limits of language. Eventually, even the ultramassive black hole at the center of IC 1101 would slowly shrink and end in a final burst of quantum energy. The giant, built across billions of years from the accumulated remains of countless smaller galaxies, will eventually leave nothing behind. The universe is not a museum of finished objects. It is an ongoing process in which even the grandest structures are temporary arrangements of matter and energy, slowly dissolving across unimaginable stretches of time into a quieter and colder cosmos. There is something worth pausing on before we finish. When we observe IC 1101 today, we are not seeing it as it currently exists. Light travels at a finite speed, and the light now reaching our telescopes from that distant galaxy left its source more than 1 billion years ago. What we observe is not a current portrait, but a historical document, a frozen snapshot of the universe as it existed 1 billion years in the past. This means that when we study the most distant objects in the universe, we are automatically studying the ancient universe. Distant space and distant time are the same thing when light is your only messenger. The telescope is in that sense a genuine time machine, and IC 1101 is a relic, a preserved chapter from a cosmic story that has continued past the point we can see. Every feature we measure in IC 1101 is a message from the past. The depleted core is the signature of ancient black hole mergers. The smooth elliptical shape is the aftermath of countless collisions that erased all spiral structure over billions of years. The diffuse outer halo is the accumulated graveyard of smaller galaxies that fell too close and were consumed. The hot surrounding gas is the residue of billions of years of gravitational energy. Nothing about IC 1101 is accidental. Every detail is a record of a long process playing out across cosmic time. Here is the final thought, and perhaps the most important one. On a rocky planet orbiting a completely ordinary star, in the outer regions of an unremarkable galaxy, a species that has existed for a cosmically negligible length of time has looked out into the deep and found IC 1101, has measured its distance across more than 1 billion light-years of space, has estimated its total mass, has inferred the history of its mergers and the probable scale of its central black hole, has placed it within its cluster environment and traced that cluster's connection to the cosmic web, has even begun to reason carefully about its fate billions of trillions of years from now. That is not a small thing. The universe produces structures so immense that they genuinely exceed the comfortable reach of human imagination. And yet, inside that same universe, on a world that would be completely invisible from IC 1101's location, even with the sharpest possible instrument, something capable of asking questions about those structures arose. Not through revelation, but through patient observation, careful measurement, and the long, slow accumulation of understanding built by many people across many generations. IC 1101 is bigger than any image the mind can contain in a single thought. You can read the numbers. You can study the descriptions. You can build comparisons using every familiar scale you know and still end up far short of the reality. The scale genuinely exceeds what the imagination can hold all at once. But you can follow the story. You can understand how gravity operates in a cluster environment over billions of years. You can picture what it means for galaxies to merge and reshape each other across cosmic time. You can grasp why the center hollows out, why the halo extends, why the surrounding gas stays hot, and why the whole vast system slowly ages in the expanding dark. Once you can follow the story, something changes in how the object feels. The galaxy is no longer merely a number. It becomes a narrative, a process, a history written across unimaginable distances in ancient light. Out there in the deep, more than 1 billion light-years from this small planet, the giant still glows. Quiet and vast and deeply old, no longer unknown, no longer merely a faint blur in an old catalog. A world built from worlds, a history assembled from the histories of countless destroyed galaxies, one of the most extreme visible objects the universe has so far produced in all of its long existence. And we know it is there. That, in the end, may be the most extraordinary scale in this entire story. not the size of the galaxy, but the reach of understanding. The universe can construct structures larger than imagination can hold, and still leave room, inside that same universe, for imagination to arise and reach toward them. If you found this journey worthwhile, leave a like and subscribe. There is always more waiting in the dark.